want to do today is talk to you about sort of two different concepts in physics. So we're both physics majors, currently in an optics class at Carleton. And our job today is just sort of to describe to you two kind of interesting bits of physics and how it fits into optics. So I'm going to start by showing you guys a quick video. I don't know if you guys have heard of minute physics on YouTube, but if you haven't, no worries. But it's sort of like a minute physics style video about the Doppler effect. I don't know if you've heard of that before. And then we'll just talk about it, talk about what you think. So, get started. It worked. Okay.
Standing on the sidewalk as an angry driver rushes past, blaring on their horn. And you wonder to yourself, what's going on? Why does the pitch change? Well, this has to do with some physics. Let's consider a single person making a loud noise and standing still to figure out how sound waves are working in this scenario. Your friend's mouth produces sound waves. There's multiple waves that I'll draw here. And this sound propagates through the air to reach your ear. Now, these three crests that I've drawn here illustrate the beginning of each wave, and the distance between them is called the wavelength. This is important because the wavelength can tell us something about the pitch or the tone of the noise. If we draw a quick graph, we can see that they're inversely proportional, which means that for a very large wavelength, we'll hear a really deep or low sound. And for small wavelengths, we should hear a very high-pitched sound. So now that we have an idea of how sound works when we're standing still, let's consider the scenario where your friend starts to run away. It's probably a little bit louder than whatever they're running away from. At some time 0 in the beginning, they'll be simply standing still, and they'll produce a single wave. Sometime later, they'll have moved a little bit more forward, and that wave will have propagated through the air a little bit more further, making a larger circle. They'll also produce a second wave at their new location. As time passes, these waves will continue to propagate further and further away, but maintaining their same spatial position, their same spatial center, as our person continues to move farther and farther away. Notice that the waves are starting to clump in the front, such that we have a small wavelength. In the back, they've actually spread out because our object is moving, creating a larger wavelength. What does this mean for our car scenario? Well, if we're standing in front of the car and it's driving towards us, we should see that we have very small wavelengths because we're in front of the moving object. If we're behind it and the car is driving away from us, we should see that our wavelength is much larger because we're behind the moving object. Therefore, in front, we should hear a high-pitched sound, and behind, we should hear a low-pitched sound. Can you hear it? This phenomenon is what physicists call the Doppler effect.
Okay, so the idea behind this style of video is to present physics and physics that might be slightly more complicated than we're used to in a really kind of quick format. So what I thought would be fun now is if you guys have any questions about the Doppler effect, or if all of you have heard about this before and you think it's totally boring, I would love to hear from you, and then maybe we can break up into whatever pods you're in, and you guys can discuss sort of applications, like why is the Doppler effect even useful, why do we care about it? We can sort of have a bigger classroom discussion. Does that sound like something we could do? That's a head shakes of no. Some recognition that you've heard what I said out loud. Okay, cool. So do you guys have any questions? Is this just something you've all heard before? Again, nods of heads, shakes of heads, some recognition that I understand that you heard what I said out loud. I can wait. Yeah? few people are nodding, some people are shaking their heads. Okay, so why don't, in your pods, if you don't mind moving over to maybe the table next to you so you have somebody to talk to, let's work and think about the different, why we might want to use it. So we're going to take like 1 or 2 minutes and come up with a few applications of the Doppler effect. If you can't think of an application, think about why it's hard. So try to figure out a reason why you can't come up with something. And that shouldn't be like, we can't think of anything, but like a physical reason why it's hard. Okay? All right. Go. Begin.
Already had enough.
What?
Oh, God.
So we take like 1 more minute, and just so you guys know, we're going to go around, each table is going to share, so you might want to make sure that you definitely have something to say.
We had a request for, what was the question again? They weren't paying attention.
So I want you guys to think about an application of the Doppler effect. So why it might be useful, why we actually care about it, right? The phenomenon that I talked about in the video. And if you can't think of an application, why is it hard to think about an application? Does that make sense? Take another like 30 seconds. This one group was confused. Gather your thoughts.
Because if you're a bat, you have that correlation, and you can see how far things away.
Just want to say domino effect.
Okay, so let's all come back together. Everybody eyes front. And starting, I guess, with this table. Why don't you guys tell us what you were thinking about?
Well, it made us think of bats because they use sound to figure out where they are, and it helps us figure out where things might be.
Yeah, sure, you can use it for sonar.
Yeah.
Totally. What about you guys?
Maybe like see how far away it is, something.
Okay, yeah, similar idea. Totally. What did you guys talk about?
Maybe. High-pitched sounds are harder to hear farther away, so when high-pitched sounds are closer, it's better to hear the sound. And when loud,
I got nothing.
what's the opposite of high-pitched? Low-pitched?
Yeah.
Low-pitched sounds are farther away from you, it's better to hear.
Okay. What did you guys think about?
It was hard for us because we don't have background information about it.
Okay. So like, what kind of background would you want? And other people can jump in here. Yeah, it's kind of a hard question, right? I think the hard part about physics is that sometimes we study all of these different systems and we don't really think about why we care beyond because we're physicists and we happen to think that it's really, really cool, right? And so it's a really important question to keep asking yourselves. Let's keep going around, but I want you to think about what kind of background information you would have wanted. All right, let's go on with this table.
Yeah, we were thinking bats too.
You guys were also thinking about sonar? Okay, cool. What about you guys? Everyone thought about sonar. What about you guys? You think about it?
too.
Okay, cool. So one other application that we can talk about, which is actually what my project is currently focused on, is that not only does sound have a wavelength, right, and propagate like a wave, but also light has a wavelength and propagates like a wave, right? And so with, have you guys ever heard of photons? Shake your head. Some acknowledgement that you heard what I said. Cool. So photons are going to have some wave-like behavior, right? They have some associated wavelength with them, right? Because we can model light as both a wave and a particle. And that means that if we have a beam of light, for example, it's going to perceive other moving objects as having different wavelengths. So not only do we have like wave-particle duality in light, but we also have wave-particle duality in matter. So all matter has this wave-like idea, which is totally trippy to think about, and ends up getting into some really weird quantum physics. But what my project is orienting around right now is talking about what happens when we can actually study this wave behavior of matter. And it turns out that there's this method called Doppler cooling, where you actually use the interaction between photons and atoms to cool down the atom. And that might sound really weird because we usually think about light as heating stuff up, right? Because it sort of, when I think about hitting an atom with a photon, have you guys thought about that interaction before? No? Yeah, so it's actually really weird, and this is something you'll probably come to later in class. But it turns out that when you, that atoms and electrons can actually absorb the energy of a photon. And this sort of increases the energy of the atom and gives it much more kinetic energy. You guys talked about kinetic energy yet in this class? No? Maybe a little bit? Itty bitty bit? So kinetic energy relates to how fast things are going. So basically this means that if we hit an atom with a photon, usually we associate that with the atom increasing its own energy and moving more quickly. But it turns out that if you hit opposite, it acts kind of like if you threw a bunch of bowling balls at a car. Right? If you threw a bunch of bowling balls at a car that was rolling towards you, what would happen? What would you say?
Slow down.
Yeah, it would slow down, right? You're just throwing all this force at this car. It's the same idea with the photons. But we have to take into account the Doppler effect, because there's this really weird shift that happens when you're moving and your wavelength actually changes. So, while normally you need to be at a really specific energy with these photons in order to slow down the atoms, you actually can change that energy, and you have to adjust the level given the speed that the atom's actually moving towards you. So the Doppler effect becomes really handy and really weird when we start looking at quantum effects of physics and more optical systems. And this might start to make more sense as we go on, as you guys continue in physics throughout the year. But it's sort of a glimpse at what you could do with physics afterwards. These optical setups take up like enormous rooms of just aligning mirrors and craziness, and it's pretty cool. Do you guys have any questions for me, or we can move on to John's presentation? Okay, cool. Well, thanks for your time.